Welcome to chapter 14. This chapter is about the ANOVA, analysis of variance. It's a super important analysis method in statistics. So let's begin with exercise 1. The goal of exercise 1 is to implement the ANOVA math yourself without using Penguin or stats models or any other library that will compute the ANOVA for you. Now, in practice, this is not something you generally want to do. For a simple one-way balanced ANOVA, it's actually pretty straightforward to implement the ANOVA yourself. But as soon as you start getting into multifactorial ANOVAs with interaction terms and so on, the math gets pretty hairy. It's going to be super easy to make a coding mistake. So basically what I'm trying to say is write out the math of the ANOVA for this exercise and then never do it again. But working through this exercise, I hope, will be a really great educational experience for you where you will really feel like you understand how the ANOVA works. So we'll take some of the mystery out. Okay, so earlier in the chapter, I gave this funny example experiment of casting spells and which kind of magical beast can cast more spells per minute. Here are the raw data. Obviously, these are fake data. Also pasted in the online code, so you don't have to write out all of this stuff here. Let's see. So you want to do a couple of things. Create figure 8. I will show you that figure in a moment, and then implement the formulas in Python code to perform a one-way ANOVA, and I'll show you that figure, which is the table that shows all the equations in a moment. Okay, so then basically you want to create a ANOVA table that looks something like this. Now, these are not random numbers. I'm giving you exactly all of the raw data. So you should be able to reproduce these numbers exactly. All of it, the p-values, everything, you should be able to replicate these numbers exactly, including these two measures of effect size. So here we have figure 8. This shows the data, visualizes the data as bar plots. So you can see the number of spells cast per minute on the y-axis, the 3 different types of magical beasts on the x-axis. And I have error bars indicating the standard errors of the mean. And then I print out the means and the sample sizes for each of these 3 categories, each of these 3 types of creatures. Okay, so this is part of the goal of exercise 1, to write code to reproduce this graph. Here is figure 4, which shows all of the formulas to implement the ANOVA table. So we have the between sum of squares, the within sum of squares, and the total sum of squares. So the between sum of squares is the mean of each category. In this case, that's the mean of our different magical beasts minus the grand mean, and then that squared, and then multiplied by the number of elements in each category. And we actually do have an unbalanced design. So this is either going to be 14 or 13, depending on the creature type, depending on the condition or the category, the level of this factor. Okay, so basically that accounts for differences in sample sizes across different levels within a factor. And then we have the within, and that you can see is the difference between the individual data points and the category mean or the level mean. So this term here is the same as this term here. The grand mean, the total mean of the entire data set, is actually not present in this sum of squares within. And then here we have the total. Now there's a little trick to compute the total, which is you don't actually need to implement this formula. And that's because we know that the total variance gets decomposed into the sum of the SS between and the SS within. So once you've calculated these 2 terms, you just add them up and that gives you the total. Or if you prefer, you can compute SS between and SS total and then subtract between from total, and then you get the within. Anyway, here's the degrees of freedom. K is the number of levels in the factor, which in our case is 3. Here's the total number of data points in the data set. And then we use the degrees of freedom to normalize the sum of squares, which gives us the mean square. And the ratio of these 2 is our F statistic. So you can see it's not so bad to implement this in Python. It gets a little bit tedious, but you have to make sure that you're writing the code correctly and not forget, this N sub j term here is easy to forget and to leave out accidentally. But otherwise, I think you won't struggle too much with this exercise. Here are the raw data. Here I'm, for convenience and also for visualization, I'm getting the sample sizes, the means, and the standard errors of each of these three levels within this category. Here is where I create the error bar. So let's see, creating the error bar itself is fairly straightforward. The x-axis is just the numbers 0, 1, 2. And then the y-axis is the means. And then we have the y-errors is the standard errors of the means for each category. And then here I'm drawing in the text. So the x-coordinate is 0, 1, or 2. And here for the height, I'm just specifying the average of the height. So basically it just plots it in the middle of the bar. And then, yeah, I print the mean and the sample size. Okay, so that's basically it. I think this is pretty straightforward code if you're familiar with matplotlib. Next, we get to the actual ANOVA. So here's what I do. To implement this, there's multiple correct ways to implement this. If you did it in a different way than I did, that's great. That's totally fine, as long as you still get the right answer in the end. Okay, so I put all the data into one vector. That just makes it easier to compute the total mean. And yeah, here I have the for loop to calculate the sum of squares between. So you can see that I'm looping over the three different groups. And I say the group mean minus the grand mean, the total data set mean. Take that difference and square it, and then scale it by the length of the group. So the number of elements in each group. And then we just keep summing that. And that is the SS between. Here for the list comprehension fans out there, I rewrote this for loop using list comprehension. This is fine if you like list comprehension. Sometimes I use list comprehensions, sometimes not. In this case, I actually prefer the for loop. It's more lines of code, but I think it's much clearer and easier to read. Harder to make mistakes this way, but yeah, I mean, this is also fine. Okay, here we have the SS within. Again, this is pretty straightforward. So it is the all of the differences of the individual data points minus their mean. So not the total mean, but just the within category mean. Square all of those and then sum them up and then add all of those up across the different conditions. So this is the, remember when I showed the equation in the book figure, there's two summation signs. So this is the summation sign for within each category, and then the summation across the different categories. So that's the second summation sign. That's actually just hard-coded to say, this plus this here. This is the summation here plus this. Obviously, this code is hard-coded for this particular example. So if you would use a different example, different data set with two categories, and this code is not going to work, but that's totally fine. This is, as I mentioned, this is not code that you would use in practice. This is code that you use to make sure that ANOVAs become easy to understand and sensible for you. Okay, so here, as I explained, we don't need to explicitly calculate the SS total. Once we have any two of these categories or these terms, we can compute the third. Okay, so let's see. Yeah, degrees of freedom term. Here I calculate the mean square terms, which is just the sum of square terms divided by their degrees of freedom. And then we get the F statistic, which is the ratio. And we use f.cdf to get the p-value corresponding to this F value with these two degrees of freedom. And then, yeah, here I'm printing out the ANOVA table. It takes a little, it's a couple minutes of kind of tedious finagling to get this table to work with all the spaces and so on, but it's not so bad. Okay, and then here we have the effect size. So eta squared, that's the simple version of the effect size. It's just the ratio of SS between to SS total. So basically how much of the variability in the data set can be attributed to differences between the group means. Now, as I mentioned in the book, this term eta squared is biased, so it's going to overestimate the actual amount of variance explained. And so that's why we also compute omega squared. Now, in practice, you you wouldn't really need to compute eta squared. You can do partial eta squared, which is the same thing as omega squared for a simple one-way ANOVA. But you can see that this is a bit of an inflation here. So this is not a huge increase, but basically this is a bias term. It's inflated, and this is a better measure of the amount of variance that is explained due to our conditions. And basically what this tells us is that 14%, let's round it up to, let's say about 15% of the variability in the spells cast per minute can be attributable to the differences between categories, which in this case is the different magical beasts. So that also means that 85% of the variability is due to other factors, contextual factors, genetic factors, I don't know, individual differences, all sorts of other factors. Obviously, these are made up data. It's just something a little bit silly, but that is how you would interpret this kind of a finding. Welcome to exercise 2 of chapter 14. This is a follow-up to the previous exercise because in the previous exercise, we implemented the entire one-way ANOVA from scratch by implementing the formulas directly. As I mentioned multiple times, that's something that's it's a great experience to do when you're learning about ANOVAs. When you finish this book, you basically never want to implement an ANOVA formula yourself. You always use some kind of a library or software. In this textbook, I use the Penguin library a lot for ANOVAs. Although in the code, I'm also going to show you how to implement this using stats models. But Penguin is great for ANOVAs. Okay, so it's pretty simple. All you have to do in this exercise is to reproduce the findings you got in the previous exercise, but using Penguin. And then what Penguin also allows you to do is compute all the post hoc tests using the Tukey correction for multiple comparisons. You should see that you should get a output that looks something like this. I will explain this table, how to interpret it, and what it means, and what conclusions we can draw from these post hoc tests when I produce this in Python. So the main point of this entire code cell here is just to get a data frame, a pandas data frame that contains all of the data. So in the previous exercise, we were just using NumPy arrays to implement all of the ANOVA formulas. But to use Penguin, you really want to have the data in a pandas data frame. So here I'm putting all of the data together. These are the group labels. So we have N elves times the word elves, N dwarfs times the word dwarfs, and N trolls times the word trolls. And then here I'm using plus sign to concatenate. So this is not adding them together, it's concatenating the strings. Okay, so then it's pretty straightforward. I create this data frame. Here you see some of the elements in this data frame. So I'm just skipping every sixth element. Super simple data set, but this is the way to get started. Okay, and then performing the one-way ANOVA is really simple. We say PG, that's the typical abbreviation for Penguin, .ANOVA. And then we specify the data. Detailed equals true basically just gives us a little bit more information in the ANOVA table. We have to specify the dependent variable and the between subjects variable. And this is, these are directly coming from the labels of the columns. Okay, so then I'm just printing out the result. Okay, so we see you can confer back to the results from the previous exercise, same exact results. And so in terms of the numbers, it's not so interesting, but I think you can see that this is a much better way to implement an ANOVA than writing out all the formulas as we did in the previous exercise. Okay, this is, okay, so this cell is exactly the same thing, just without detailed equals true. So here it's detailed equals false. And you can see that basically it's just not giving you the within subjects sum of squared terms. And that's because, there's nothing to statistically evaluate here. Okay, so then we have the actually, maybe I'll show this first. So this is a function OLS, which comes in the stats models library. And you can see the code is, I think this part is nice. because you can literally write out the model, the equation, but it's more object-oriented approach to fitting models. And then we use statsmodels.stats.ANOVA. The LM is for linear model. And yeah, you can see this is the same thing. So maybe you prefer stats models. That's great. In this chapter, I'm mostly going to be sticking with the Penguin library. Okay, so anyway, here I'm doing all the pairwise tests, post hoc tests, using the Tukey method to correct for multiple comparisons. Again, just specifying the dependent variable and the between subjects variable. This here .round 3 is just to round the decimal points, just so we don't get really long numbers. You can see if I get rid of this, then it's just, I mean, this is also fine, but this is more numbers than I think we really, higher precision than is really necessary here. Okay, so how do we interpret this this table here? So you see here, the first two real columns give us all the pairs of variables. So these are the condition comparisons of elves versus dwarves, elves versus trolls, and dwarves versus trolls. Then we also get the means printed out, which is important because that helps us interpret the results. Here you see the p-value. This is Hedges H. I'll talk about this in a second. So this p-value is the corrected p-value. So this we can directly interpret. So this is a p-value very close to 1. So this tells us that elves and dwarves have a comparable number of spells that they can cast per minute. This one is significant. So that tells us that elves and dwarves are different. Now, this p-value, of course, doesn't tell us the direction of the effect. The t-value also doesn't tell us the direction of the effect because we don't know immediately which, what the numerator was, which condition was subtracted from which other condition. So that's why it's really useful to have these means printed out. So we can see that elves cast 4 spells per minute more than trolls. I love talking about this data set. It's hilarious. Okay, then we see dwarves and trolls. This is actually not statistically significant. It's close. If this were a very interesting or theoretically important finding, we could interpret this as being marginally significant. So we say statistically significant if the p-value is less than 0.05. If it's between 0.05 and 0.1, you can call it non-significant if you don't care about it. Or if you care about the finding, you can call it marginally significant. Okay, so then Hedges H. This is a measure of effect size. It is not bound by 1, like eta squared or partial eta squared. Instead, it's comparable to a Cohen's d for a t-test. So it can exceed 1. It just happens to be, in this case, that we get a value that's very slightly less than 1. Now, it's pretty interesting to see that the t-value and the Hedges H are really, really similar for these two comparisons, but this one is not statistically significant just because the effect was just not quite big enough. The goal of exercise 3 in chapter 14 is to demonstrate empirically in simulated data that the t statistic and the f statistic are very closely related to each other. In fact, if you have a one-way ANOVA with 2 levels, so 1 factor and 2 levels, then you can do an ANOVA or you can do a t-test, and those are exactly the same thing. So in fact, the f statistic is the t statistic squared, and that is exactly what you will demonstrate here. Okay, so what you want to do is simulate 2 groups of data, so 2 samples, one with a sample size of 30 and the other with a sample size of 35, one having a mean of 4 and the other having a mean of 6 and a standard deviation of 2 for both groups. In truth, it doesn't actually matter how you simulate these data. The only really important thing is to have 2 groups of data samples. Okay, and then import those data into a pandas data frame, and then perform an independent samples t-test and a one-way ANOVA, and then get the t-value and the f-value, both p-values, and print them out. So you can see in this case, the f statistic was 20.666, slightly ominous number, but that's just how it worked out in this sample. The t-value was minus 4.55. Now, obviously, these are not the same numbers. You know also that t-values can be negative, f-values cannot be negative. They're strictly non-negative values. But we don't want the t value per se, we want the t value squared. So if you square this t value, you're going to get exactly the same numerical value as the f statistic. So write some code to produce this output to demonstrate to yourself that the t statistic and the f statistic are basically the same for a one-way ANOVA with two levels. Obviously, you can only demonstrate this for one factor and two levels because the t-test is only defined for two levels. So anyway, or two groups. So here I have the two means. I'm soft coding all of this because I guess, first of all, soft coding is just good coding practice in general. But as I mentioned many times before, I don't want you to have this code and just run it and then forget about it. I want you to work with this code, explore it, change the parameters, try all sorts of different things, anything you like. Okay, here I generate the two normal distributions and then put them into a data frame. So you can see what that data frame looks like here. It's not a terribly interesting, not super complicated data frame. The dependent variable is called the data, and the IV is called a group. Anyway, here I'm using stats.tTestInd to test for the different, to implement the t test for these two different groups. And here I'm implementing this using Penguin as an ANOVA. So I'm running these, and then here I store the results in separate variables here. And then in this code cell, here is where I'm extracting all of the information. So I have ANOVA here. I'm getting the denominator degrees of freedom, or sorry, the numerator degrees of freedom, the denominator degrees of freedom, and the F value, so the F statistic and the P value, comparing that to the T value. This is the raw T value. And then here I have the T value squared. Obviously, because these are random numbers, we're going to get a different result as the one I showed in the book, but that doesn't matter. What matters is that the T squared is the same thing as the F value. Exercise 4 of chapter 14 is a pretty interesting exercise. The goal is to explore the impact of a small number of outliers in the data on the statistical significance of an ANOVA. Now, because we are simulating these data, we can control any and all of the parameters that we want, which is great. So we are going to simulate a situation where there should be no statistically significant difference between any of the conditions because we are literally drawing random numbers from exactly the same population. So we expect 0 statistically significant results, and then we're going to put a few outliers into the data set, and then we're going to see what happens. Maybe we still get non-significant results. Maybe we start getting significant results because of the outliers. Let's see what happens. Okay, so here is the goal. There's two parts. We're going to start with this exercise by just writing some code to explore qualitatively what happens. And then the second part of this exercise involves writing more code to run an experiment to get a little bit more of a rigorous, systematic overview of the impact of outliers on an ANOVA result. So the first part is to simulate 3 groups of data, so 20 samples per group, using data sampled from a standard normal distribution. They all have the same expected mean and expected standard deviation. So we're creating 3 groups that are drawn from exactly the same distribution, and then putting those in an ANOVA, a one-way ANOVA with 3 levels. We certainly do not expect any significant differences here. Okay, and then here is the key point. Replace the last 2 data points of group 3 with the number 10. So the number 10, because these are data drawn from a population with a standard deviation of 1, a numerical value of 10 is 10 standard deviations larger than the mean. So these are actually pretty big outliers. Okay, so once you've created this data set, put it into Pandas, and then run a one-way ANOVA. And then we just want to see whether the F value has a corresponding P value less than 0.05. Okay, so there's more to this exercise, but first I'm going to switch to Python and show you the code for this part of the exercise. here you can see that I'm generating all the data as a random numbers drawn from a normal distribution. It's a standard normal distribution. The size here is 3 times n, because here I'm specifying the sample size per group, not for the total sample size. Okay, and here is where I replace the final 2 data points with outliers. Here I say fixed to 10 because in the next part of this exercise, we're going to vary this number a bit. Okay, so yeah, group labels, import it into a data frame, and then we can run an ANOVA. So in this case, the p-value was greater than 0.05, so not statistically significant. That's actually really good. That's what we expect. Run it again. Again, non-significant. Let's see, I'm just going to keep running this multiple times. Eventually, it's going to be, okay, here we go. So here we get a statistically significant result indicating that there are real differences between the means of these 3 different groups. Now, we know that that shouldn't be the case because they're all identically drawn from a standard normal distribution, but it shouldn't be too surprising that we get this result because we have imposed outliers in 10% of the data, right? So there's 2 outliers and a sample size of 20. So 10% of the data in one group have these really large outliers. Okay, so with this in mind, now we're ready for the second part of this exercise. The second part of this exercise involves taking the code that you just created and putting it inside a for loop. So we're going to run this experiment 300 times, generate new data, 300 times, run 300 ANOVAs, and we don't care about the F statistic or anything like that. We just want to know whether the main effect of the factor is statistically significant, whether it has a p-value less than 0.05. So you're going to print out something that looks like this. 81 of 300 tests, and then the percentage had p less than 0.05 with some parameters here. So obviously the results are going to change each time you run it because it's random numbers. But, what do we expect? We expect 5% of statistical errors. So we would expect that around 5% of cases had p-values less than 0.05. But because we have introduced outliers, we actually get more than 5%. In this case, a lot more. Okay, so a couple of modifications from the code you just ran. Change the sample size to 50. Previously, it was 20. Soft code the number of outliers. So instead of hard coding it to be 2 outliers, you want to have a variable that says the number of outliers to introduce. And the outliers should be drawn randomly from a normal distribution. So instead of fixing the outliers to be exactly 10, you draw them from a normal distribution that has a mean of 10 and a variance of 1. Okay, so yeah, so I have a few things to remark about this, but I will say that in a moment. Here you can see I'm soft coding the sample size, the number of outliers. Again, what I want you to do here is look at this code, understand this code, and then use this code as a springboard to continue working on your own. You can apply this code to investigate effects of outliers in, positive and negative outliers. How much do they balance themselves out? Outliers in 2 conditions instead of 1 condition, all sorts of interesting things you can do here. Okay, let's see, the number of tests. So now I loop through the number of tests in this experiment. Here's where I generate new data. Here's where I introduce the outliers at the very end, which means they're always going to go into group 3. Here's where I import the data into a pandas data frame, run the ANOVA in Penguin. And here I'm just saying if this p-value, if the p-value is less than 0.05, then increment the counter, the is significant counter. And then I report the number and the percentage here. So let's run this. Here we get 83. So very, very close to what we saw in the book. So we can run this again. You can see this is pretty stable. When you set up the experiment like this, it's fairly stable. You're always going to get 80, 90, somewhere around 25 to 30% alpha errors, type 1 errors. Now, this is entirely due to the introduction of these outliers. So for example, if we comment out this line, Now, I'm no longer introducing outliers, and let's see what number we get here. Here we get 5%, 5.67%. What do we expect? We expect exactly the theoretical average is exactly 5% of these tests should have p less than 0.05 because we are generating data from a null hypothesis distribution with an alpha of 5%. So we should get 5% of the time we see a erroneously statistically significant result. This one was a little bit higher, but that can happen. You can also try increasing the number of tests like to 3,000 instead of 300. But anyway, yeah, lots of interesting things you can try. You can see what happens when you draw outliers that are less extreme. So instead of 10, maybe we take them from 4. So this is still going to be fairly unusual, but not quite as extreme as an outlier of 10. And here I expect, yeah, more than 5%, but not quite as extreme as 25 to 30%. So I hope you enjoyed this exercise. The main take-home message is the ANOVA is sensitive to outliers. In particular, you are more likely to make false alarms when there are outliers in your data, particularly if those outliers are in one condition. Exercise 5 of chapter 14 is a little bit weird. It's kind of bizarre. It doesn't involve any coding. It just involves thinking. And basically, the main point of this exercise is to remind you and get you thinking about the two degrees of freedom parameters for an ANOVA. So we have the numerator and the denominator degrees of freedom. Now, in general, the numerator degrees of freedom is smaller and the denominator degrees of freedom is higher. That is not strictly mathematically necessary. There's no like fundamental law of nature that says that the denominator degrees of freedom must be bigger than the numerator degrees of freedom. But the way that we do experiments, that just happens to work out that way. And that's because the numerator degrees of freedom is related to the number of conditions, and the denominator degrees of freedom is related to the total number of observations. Now, in general, it basically almost always works out that you have a lot more observations than you have factors. If you have more factors than observations, then I don't know, it's just kind of weird. Okay, so let's see. You don't need to really write any code. You just need to think about coming up with an experiment design where the numerator, degrees of freedom, is higher than the denominator, degrees of freedom, like this. Okay, so yeah, this is not a good thing to have in the real world, but it's interesting to think about what kinds of conditions would create this situation. Okay, so there's a bajillion possible ways to do this. Here's one example. So imagine that there are 10 factors in your experiment. Each factor has one observation, one data point in each factor. And then we have one additional factor with 20 samples. So it's a ridiculous design and doesn't make any sense. It's not going to give you high quality data, but it does technically work out. So the numerator, degrees of freedom, is the number of groups minus 1, which is 10, right? So I hope this wasn't too confusingly written, but it's basically 11 conditions in total, 10 factors with one sample and one factor with 20 samples. So the numerator degrees of freedom is 10, and the denominator degrees of freedom is the number of observations minus the number of groups, which is 10 from the one observation per factor, and then 20 minus the number of conditions, and that gives us 19. So now we have the numerator degrees of freedom with 10, the denominator degrees of freedom with 19. Again, this is not a realistic scenario, but I hope that it helped you think more about the calculation and interpretation of these two degrees of freedom parameters. Here's the video for exercise 6 of chapter 14. This exercise follows up from a concept that I have stressed and we have also empirically demonstrated a few times before in this book, and that is the relationship between p-value and effect size. So you might remember we explored this relationship in the chapter on t-tests. Now we're doing it here. You'll see this again. in the chapter on regression and general linear model. The idea is that a p-value is not the same thing as an effect size. Having a small p-value does not necessarily mean that the effect is big. It just means that it is unlikely to happen given the null hypothesis. Okay, so, that said, there actually is a relationship between p-values and effect sizes, but they're relatively constrained to holding certain features constant, and this doesn't really happen in practice. So we are going to discover this relationship in this exercise in the context of an ANOVA. So here's what you want to do. Simulate two groups of data from normal Gaussian distribution, standard deviation of 1, and 10,000 samples each. So 20,000 data points in total, 10,000 per group. So the mean of group 1 is 0. The mean of group 2 is 0.1. And so 0.1 we can actually interpret in terms of a standard deviation. So that means that the difference between the theoretical population means of these two groups is 1/10 of a standard deviation. So that's a very small effect size, right? 1/10 of a standard deviation difference between the two groups. That's a very small difference. Okay, but it's a really big sample size. So then run the data through an ANOVA. It's a one-way ANOVA with two levels in one factor. So, and then you can just observe the p-value and the partial eta squared. Here, this is percent. So this is 1/3 of 1% of a effect size. This is an absolutely minuscule, infinitesimal effect size, and yet the p-value is wildly significant. Okay, so there's more to do in this exercise. There's actually multiple parts to this exercise. I'm going to go back and forth between the book and the code. So right now I'm going to switch to code and implement this experiment that I just described. The implementation is quite straightforward. Here I specify a sample size of 10,000. Here we get data 1 and data 2. And yeah, you can see using parameters that I said in the book. Concatenate them into one vector, create group labels, so group 1 times n, and then group 2 times n. Here we have the data frame, and then we simply run an ANOVA in Penguin. Very straightforward. Okay, so again, here we see the p-value is really, really small. It's 10 to the minus 12. And the partial eta squared, or the effect size, is 0.2%, right? So this is partial eta squared in proportion. And then we can multiply it by 100 to get 2%. So this is 0.2% of an effect size. It is absolutely tiny. It's so small that, there's really no practical application of something with such a tiny effect size. And, you can see the effect size is small here, but the reason why it's so highly statistically significant is because the sample size is so huge. So we can do a sample size of 100, which is still a pretty respectable sample size. And now we get still a significant p-value. And, a lot of studies have sample sizes in the range of, let's say, 60. This is actually a sample size of 60. It's 30 per group. That's a pretty respectable sample size. And here we see that the p-value is not even close to being significant, although here the partial eta squared is actually higher than it was that first time when the p-value was absolutely infinitesimal. So this is just, this is how it goes in statistics. When you have a really, really large sample size, the p-value can be very, very tiny. So the next part of this exercise is basically to take the code that you just ran, put it inside a for loop over 300 repetitions. Now, the only thing I want you to change here is the mean difference, the expected mean difference. So instead of having the data from group 2 drawn from a population with a theoretical mean of 0.1, here you should use 0.01, so 0.01. So now we're talking about 1% of a standard deviation, 1/100th of a standard deviation difference between the two population means. And then, so then you run the ANOVA 300 times and store the p-value and the partial eta squared from each of these 300 iterations. So then you can report the total number of tests that had a significant result. And then I want you to plot them, and you can plot them like this. So here we have the partial eta squared. So these are the effect sizes on the y-axis. And here in panel A, the partial eta squareds are separated according to whether the p-value was less than 0.05 or greater than 0.05 over here or less than 0.05 over here. Actually, maybe it makes sense to have this be the other way, right? Less than 0.05 would be on the left. But anyway, you can swap the order if you want. And then over here, we have the graph of p-values by the partial eta squared. Now, I am going to have a few words to say about this when I show you the code. There's more to do in this exercise, but again, I'm going to switch to Python, show you some code, make some interpretations and some discussion points, and then I'm going to come back to the book for the rest of the exercise. All right, so here again, redefining the sample size. That's actually because I'm going to change this later, but here it's reset to 10,000. Okay, so here we have 300 tests and initializing p-values and partial eta squared. So in a for loop, then we simulate the data exactly how I did it before, but just the mean offset here is smaller. Okay, so then we create the data frame, run the ANOVA, and then we store the p-value uncorrected and the partial eta squared, and then I multiply this by 100 because I want the percent instead of proportion for no particular reason. All right, so run all of that code. This takes a good couple of seconds here. And then here we see that almost 10% of these simulations had a significant result. So this is pretty interesting because we know that these data really truly are drawn from populations with different means. So the means are really different between these two populations, but the effect size, the true population effect, is so tiny. It's really, really, really small, but the sample size is really, really, really big. So we do get 10% of the time we can identify a difference between these two groups. Okay, so let's generate that plot over here. So again, here you see the effect sizes for the tests with a significant F value, F statistic, and here for the non-significant effects. Now, it's not that surprising that when you get p less than 0.05, the partial eta squared is larger. But you can also see, again, this is in percent. This is a fraction of a percent. These are minuscule effect sizes. Okay, so here is something interesting. So we plot the effect size by the p-values. This is, again, one of these cases where it looks like there is a really tight relationship between the p-value and the effect size. In fact, so it's a nonlinear relationship, but the conclusion from this graph would be that p-value is basically redundant with the effect size, and we don't need to calculate the effect size. We just look for smaller p-values, and that corresponds to bigger effect sizes. Now, here's the thing. That interpretation is true, but it's much more nuanced than this. It's much more complicated than this. This relationship between p-value and partial eta squared is only so tight here because we have fixed the sample size and we have fixed the population means. If we were to change the sample size, then we would not find this kind of relationship. So this is the sort of relationship that you could identify with simulated data, but is not the sort of interpretation that you can make in real experiments where you don't have control over the effect size across different studies. Okay, so let me switch back to the book to guide you through the next part of this exercise. So now what you want to do is copy and paste the code from the experiment and make a little bit of a modification. So what you want to change here is the sample size. So instead of fixing the sample size to be 10,000 in all cases, you want the sample size to be a randomly selected number between 10 and 10,000 for each iteration. So that means each of these 300 repetitions in this experiment is going to have a different sample size. And then you want to reproduce this plot, exactly this plot, and let's see what it looks like. So here I have that code. I literally just copied and pasted from the previous couple of cells. So this is all the same. Okay, now here we have I'm redefining n. Instead of fixing it to be 10,000, I'm setting it to be a random integer between 10 and 10,000. So then I define the groups, the group labels, and then here you can see is data. So this is the data from group 1, and then this is going to be some, some random number. And then here I have from data 2. Now I didn't specify in the book what the population mean of data or the data for group 2 needs to be. So you can set this however you want. I set it to be some random number squared. Basically, this is going to generate a random number between 0 and 1, and then squaring it basically just biases the result towards smaller numbers. This is just, there's this what you choose here doesn't really impact the result that you're going to get. Okay, so then the rest of this is exactly the same. And let's see, in this case, there were 80% had a p-value, and this n is actually not really accurate. This is just the final n here from the last iteration. So we see lots of these tests were statistically significant. That shouldn't be so surprising. The sample size is variable, so it's a little bit unpredictable, and there really is an effect to find. Okay, so now let's recreate the graph. And here we see, so first of all, you got a warning, but that's because I'm plotting here the log of the p-values and not the p-values themselves, and that's because there are so many significant results that a lot of p-values were really, really small. And so when you have really, really tiny p-values, it's just easier to take the log transform, as I've discussed earlier in the book, that just stretches out the lower bound here. Okay, so we see, this is not so surprising. There's a larger range of partial eta squares. Here we actually do get a lot of runs with a, respectable amount of variance explained. So this is a pretty good amount of effect size measured over here. Okay, but here is the important thing. Here we have the p-values, so the log of the p-values on the x-axis, and partial eta squared on the y-axis. And the key thing to observe here is that there is no longer a straightforward relationship. So just knowing the p-value doesn't really tell you anything about the partial eta squared, the effect size. The p-value can be relatively large. It can be really, really tiny. That doesn't tell you exactly what the effect size is going to be. You can have a really big effect size or really tiny effect size with exactly the same p-value. And so this shows that although there is a relationship between p-value and effect size, it is nuanced. It can really only be discovered in simulations or when looking at the math and keeping lots of variables fixed. In practice, you cannot assume any relationship between p-value and an effect size, and so you cannot infer an effect size based on a p-value. Exercise 7 and also exercise 8 go hand in hand, both conceptually and in terms of the code. So I recommend setting aside some time to do both of these exercises at the same time, or one right after another, but in the same session. Okay, so let's get started with exercise 7. Here, the question is whether it actually matters if you do a repeated measures ANOVA or a between subjects ANOVA if the design is repeated measures. So imagine you've measured data from the same individuals on 3 different occasions. And does it really matter if you set up the analysis as a repeated measures or as a between subjects? Obviously, if it's repeated measures data, then you should use a repeated measures ANOVA. It seems obvious, right? But the question here is basically helping you understand the real impact, the real value of a repeated measures design. And that's all about individual differences. And I will get to that by the end of the next exercise. Okay, so here's what you want to do. Create a NumPy array of 30 by 3 matrix. So this corresponds to simulating 30 observations and 3 different conditions. All of these numbers come from a standard normal distribution, but we want to simulate some condition differences. Maybe this is increased performance over time after training, and you measure your human volunteer research participants 3 times. So what you want to do is add 0.25 to all the data in the second column and add 0.5 to all the data in the third column. So now we are imposing a condition difference, a linear increase in the data values over the course of the 3 different observations from these same 30 individuals. Okay, so then what you want to do is import that matrix into a pandas data frame and convert that data frame into long format. So that means that instead of the pandas data frame being 30 by 3, you actually need a 90 by 3 data frame, 90 observations, and then in one column, and then in the second column, you need to have which condition we are sampling the data from. And then the third column indicates which subject, which individual the 3 observations come from. And that's so that the repeated measures ANOVA can link together the different data observations from the same individual. Okay, and then what you want to do, this again is going to sound a little strange, but run a repeated measures ANOVA and a between subjects ANOVA on the same data set, and then print out the data tables that looks like this. Okay, so I'm going to switch to Python and show you my solution, have a short discussion about this. There's more to do in this exercise. This is just the first part of this exercise, but I want to show you this part before getting to the next part. So here again, soft coding these variables. So we generate all the data from the same population, and then I'm simulating condition differences by adding some small offsets here. So we're getting a linear increase from column 0 with an offset of 0 to column 1 with an offset of 0.25 to column 2 with an offset of 0.5. Here's where I create the data frame. And then here is how I convert it to long format. I discussed this earlier in the chapter. You can use pandas.melt to convert data from wide format, which is what we have here, into long format, which is what we have here. Now, you could have also just simulated these data right from the beginning in long format. And if that's what you want to do, then that's also fine. But the reason why I specified creating the data in this way is to give you a little bit more experience with converting between wide and long data formats, because this is something that you will really need to do in practice when you're working with real data. Okay, so here we have the columns. We have the subject label, the condition, and the dependent variable, which here I call value. Then I run a repeated measures ANOVA, where I specify that the subject variable is called subject. And then I run a between subjects ANOVA. And here we don't need to specify the subject, of course, because in this case, we are assuming that each observation or each row in the data file comes from a unique observation, a unique individual. So that is actually wrong. This is not how we're simulating the data. But it's interesting to see that the results are basically nearly identical, almost, qualitatively the same. So we get an F statistic. Okay, so this is the table, the ANOVA table with repeated measures ANOVA and between subjects ANOVA. Here is the F statistic. You can see those are really, really close. Here is the p-value. Those are extremely close. Partial eta squared, also super duper close. Not statistically significant, but that's not what we care about in this case. What we care about now is that the results, or certainly the conclusions that we draw, are not dependent on the type of ANOVA. So you can see now I'm running this again. It's still non-significant, but that doesn't matter. You can see the p-value, the F values and the p-values are really, really, really close to each other. So what this is telling us is that the ANOVA flavor, the algorithm, doesn't matter. We get the same result, we would draw the same conclusion about the data. Okay, this cell here actually has nothing to do with this exercise. This is just for your information. I'm showing you how to run the same thing, how to run a repeated measures ANOVA using stats models. That's, as I mentioned earlier in the chapter, I'm focusing on using the Penguin library because it's just really good for running ANOVAs. But you can also run lots of ANOVA models in the stats models library. So I also just want to show you the code so you have this in case you want to use the stats model. Okay, so now I'll switch back to the book and explain the next part of this exercise. So what you want to do now is take the code that you just wrote and embed it inside a for loop over 200 repetitions. So each of these 200 repetitions, you're doing exactly the same thing, the same code, the same procedures. It's just different random numbers. So you're just drawing random numbers differently. And then, of course, you want to store the p-values from both ANOVAs. So you're going to end up with a matrix, a 200 by 2 matrix of p-values from the repeated measures ANOVA and from the between subjects ANOVA. And then I want you to plot them in a figure that looks like this. So here in panel A, we see the p-values from both tests for repeated and between. And you can see that these are not identical, but they are very, very similar. Here you see a histogram of the differences. So this is the p-value for repeated minus the p-value for between. And what you see is that the differences are centered at 0 and they are not really strongly biased, right? So it's not like doing one type of ANOVA over a different type of ANOVA always gives you smaller p-values or always gives you larger p-values. It's an unbiased variability, and it's also quite a small variability. So, you might find, if I don't have code for this, but the p-value threshold for significance is here, right? 0.05. You can write additional code for this if you want. You might find a couple of cases where one analysis would suggest statistical significance of the main effect and the other one wouldn't be statistically significant, but my guess is that that happens quite rarely. All right, so here is the code for this part of the exercise. And this code is actually not very complicated. So here we have the p-values matrix that I'm initializing, loop over all of the repetitions in this experiment. And all of this code is literally exactly copy pasted. There's nothing different in the code compared to what I already showed you. Just that, I'm storing these resulting tables and extracting the p-values from the two ANOVA algorithms. So run this, and then here is the code to generate the plot. So here I'm plotting the individual p-values. You can see it's column 0 and column 1. And then here I'm taking the difference between the two p-values and making a histogram of those data. Again, what you see, the key take-home message is that they're really similar to each other. They're not identical. They are different algorithms. They make different assumptions. They estimate the variabilities in different ways. Of course, because we have simulated these data as a repeated measures ANOVA, then this is the appropriate ANOVA model. Nonetheless, the conclusion is like, hey, why do we need all this complicated stuff? Why don't we just always do a between subjects ANOVA, even if the data are repeated measures? Well, I have an answer to that question, and it's coming up in the next exercise. This is the video for exercise 8 of chapter 14. This exercise follows directly from the previous exercise, so make sure you've gone through exercise 7 before approaching this one. Okay, so in the previous exercise, we came to the conclusion, based on the simulation parameters, that a repeated measures ANOVA and a between subjects ANOVA doesn't make a big difference. It doesn't really matter which one you use. The results will be numerically different, but basically the conclusion that you will draw is going to be the same. Now, here's the thing. In that previous exercise, there was no meaningful individual variability. So all of the observations had the same numerical range. And that is basically the answer to why that happened, why the ANOVA results were comparable. Okay, so what you want to do in this exercise is basically rerun the code from the previous exercise, but introduce individual variability. So create the data matrix such that the ith row is drawn from a population with the mean of I. So that means that the data in row 1 comes from a population with mean 1. The data from row 13 has a mean of 13, and so on. So that's going to produce data sets that look like this. Now, you don't need to create this figure if you don't want to, but you can if you want to. Obviously, my code to create this figure is online if you want to see how it's done. But here we have data from exercise 7, the previous exercise. Here is the data for exercise 8. And what I would like you to notice is the y-axis here. You can see all of these data, they're drawn from a normal distribution. So they're all somewhere around, -2 to +2. But all of the individuals, the range of variability is relatively small. Here, in exercise 8, we have a huge amount of inter-subject variability. So some subjects, you can see this cyan color here, that is way, way, way higher than this subject, this dark green subject over here. Okay, so there's a lot of individual variability, but when we look at the differences between the different conditions, then we see that the results are actually pretty comparable. So the size of the differences between, for example, 2 and 0, so the third measurement and the first measurement, that is comparable across exercise 7 and exercise 8, but the total individual variability is much higher in exercise 8. Again, this is just to give you a sense of how the data will look. You don't need to create this figure if you don't want to, or just copy my code from online to make this figure. The most important thing is to have your data look like this, and then rerun the experiment code for exercise 7. So basically, rerun the experiment and the visualization that produced this figure. And I'm not going to show you in the book what that figure will look like for exercise 8. I want you to make a guess and think about what you expect this to look like, and then try it and see what you get. So here is some of the code for exercise 8. This is just illustrating the mechanism that I used to implement this, to create this data set. There's multiple correct ways to do it. You can run through it in a for loop. It's totally fine. What I did is to create normally distributed data where all of the data are from the same population with the same mean, exactly the same as in the previous exercise. And then I added this here. So what is this? This is numpy.arange over subject. So this is going to be a vector that goes from 0 to 29. And then I am endowing it with dimensionality. So bringing it from a dimensionless array, numpy array, to a matrix, to a column vector. And then with the addition here, we get an operation called broadcasting, which allows us to add the index number. So this vector gets added to all three columns within each row. So then you see the data looks like this. This is a little bit advanced, by the way, this broadcasting mechanism. If you're not familiar with that, or if you implemented it in a for loop, that's totally, totally fine. The goal here is not to have the most compact Python code possible. The goal is to understand statistics. Okay, so you can see that as the rows increase, the numbers are increasing. But importantly, the numbers are all increasing at the same magnitude for each row. So this is simulating our individual variability. Okay, this is the code to create that figure, which I said you don't need to create on your own. But yeah, if you're curious to see my code, then have a look at it. Okay, so now actually all we need to do is go back. You can see there's some comment here, which I didn't even mention in the previous video, but it's already in the code. And here I say the commented code at the end is for exercise 8. So all we need to do is boink. We just need to delete that comment, rerun the code for this experiment. And then here we have the code for this figure. And what we see, it's going to take a minute to run. What we see now is a huge difference. This is like a ginormous difference between the p-values for repeated measures ANOVA and between subjects ANOVA on exactly the same data, just with a different ANOVA algorithm. So this is like already way, way, way different from the visualization that we got, the result we got in exercise 7. And in fact, this histogram is so, you don't see this. Why is so much data missing here? Because, from the previous exercise, I hard-coded the x-axis limit, and that was more than wide enough. That was way more x-axis real estate that we needed in the previous exercise. And now we can repeat this. And here we see huge difference. All of these p-values are clustered. They're all positive, which means that the repeated measures p-value, I just saw a little typo in my code that these labels were swapped. So it should be the p-value for between minus the p-value for repeated. And you can see that these are all positive. All of these difference values are positive. So this is different from exercise 7, where we observed basically an unbiased difference between these. It didn't matter which, sometimes it was randomly higher for between, sometimes randomly higher for repeated. That's not what's happening here. In this case, all of the between subjects p-values are really, really large. They're extremely close to 1. And the p-values for the repeated are anywhere from a little bit smaller to a lot smaller. So what is the conclusion that we can draw from this and the previous exercise? The conclusions are that there are going to be situations, there are going to be certain data sets where all of the numerical values are in a pretty tight range, and there are no real meaningful individual differences. And then the repeated measures and the between subjects ANOVA are going to lead you to the same conclusion. But as soon as you have even a little bit of intersubject variability, the repeated measures ANOVA is far superior, and the between subjects ANOVA is not going to be a good idea. So always run the repeated measures ANOVA when you have a repeated design. I hope you enjoyed working through and learning from the previous and this exercise. Welcome to exercise 9 of chapter 14. The goal of this exercise is to simulate data to create an unbalanced design in a two-way ANOVA, and that will allow us to explore the impact of the ANOVA type on the outcome. So remember, there's 3 types of ANOVAs: type 1, type 2, type 3, and this really only concerns multi-way ANOVAs, in particular with interaction terms, and the different types are basically slightly different algorithms for how to compute the sum of squares. Basically, whether you compute the sum of squares on the raw data or on the residualized data, and how you, what order in which you compute the sum of squares. And I also like this exercise because it will provide you with code that you can use to simulate ANOVAs to allow you to explore other concepts in ANOVAs, like the effect size, the relationship between main effects and interactions, the impact of outliers and sample size, and so on. So at the end of this exercise, you're going to have code not only that completes this exercise, but that you can use as a template for continuing to explore ANOVAs. So here's for the specifics. What you want to do is create a data table that simulates a 2x3 between subjects ANOVA design. Now, each cell, so there's going to be 6 cells in total, right? You have 2 factors, 1 factor with 2 levels, 1 factor with 3 levels. Each of these 6 cells has a unique sample size that is randomly drawn from between 25 and 35. So each cell has a different number of observations. That's why it has to be a between subjects design. Okay, and then I want you to create the cell means to have interactions but no main effects. So here is the means that I use. You can also use these means or try using different means. But what you'll notice here is that there's 2 rows and 3 columns. So that corresponds to our 2x3 ANOVA. So the numbers here correspond to the means of each cell. So each combination of the 2 factors. Now what you see is that there is the marginal averages are all 1, right? So the average of these 4 numbers is 1. The average of these 4 numbers is 1. And the marginal average on the columns is also 1. So the average here is obviously 1, 1. The average here is 1, and the average here is 1. So what does this mean? This means that we have no main effects. We are simulating no main effects. So all the rows are equal, all the columns are equal. But you do see that there are changes in the rows according to the columns. So this is one way to simulate data where you have interaction but no main effects. So I think the hardest part of this exercise is just getting the code to work. It's not so straightforward. to define a 2x3 ANOVA with different sample sizes. So it's a little bit of finagling in Python. If you get the statistics concepts, you're comfortable working with Penguin library to compute the ANOVAs, but you're struggling with the code to create the data sets, it's totally fine. Feel free to have a peek at my code solution. Okay, so then once you have the data, you want to run a two-way ANOVA using Penguin, and you want to run 3 ANOVAs. So exactly the same data. You're not changing the data. You only simulate the data once, and then you run 3 different ANOVAs for the 3 different types. So here is type 1, type 2, and type 3. Now, when I get to showing you this in the code, I will have a few remarks to make about this. Here is the variable that I just showed in the book text with the means. So soft-coded, so it's interesting to try changing these numbers around. Okay, so here I have 2 variables that I call fact A and fact B. This is actually the number of levels in each factor. So maybe I should have named these n level A or something like that. But so this is the number of rows, and this is the number of columns. So this is the number of levels in factor A, the number of levels in factor B. Okay, and then here I'm creating a variable called cell counts, and this is the total number of cells, which in this case is going to be 6, and then numbers randomly drawn from this range. So this is going to give us 6 numbers, 6 integers between 25 and 35, and that I will use to create the number of rows in, or the number of observations in each ANOVA cell. Okay, and then this is the total number of rows in the entire data set. So here is how I create these data. The data matrix is going to be n by 3, and we need 3 columns here because we have the dependent variable, and we have the label for factor A and the label for factor B. Okay, so now I have this matrix, group means, and I need to extract the corresponding column and the corresponding cell row in here. Now, there's several ways that you can implement generating this data. You can loop over the columns and the rows separately in a double for loop. The way that I chose to implement this was to loop over the cells instead of looping over the rows and columns separately. So this is one for loop that goes from 0 through 5. So we have 6 iterations in this for loop. Here, these variables A and B are mapping the linear index onto this matrix index. So in particular, this is index 0, 1, 2, 3, 4, 5, 6, and so on. Okay, so then I get the mean of that particular cell. Then I generate random data where that mean is the center, the population mean. And then we have some variability around that mean. And here's the size. This tells us the sample size, so how many data observations are in this cell. And then I have this data matrix, which I've already introduced you to. So we have the row index, the column index, in other words, factor A level, factor B level, and then all of the data. Okay, and then here I just update this counter. Okay, so I hope that makes sense. Let me actually, before running the ANOVAs, let me actually just show you what this data frame looks like. So all the data go into a NumPy array, and then I put them into a data frame with these columns. So here we have factor A. This is level 0, level 1, and so on. This is factor B, level 0, and then it gets up to level 3. And here is the dependent variable. Okay, so now that we have the data frame, we can run the ANOVA. Again, you can see I'm running 3 different ANOVAs in here without changing the data. So it's exactly the same data, exactly the same code, exactly the same models, except for the type, the sum of squares type. So it's going to be either 1, 2, or 3. So here you see all 3 ANOVA types. And what you see is, so no main effects. The p-values of the main effects are all above 0.05. And the p-value of the interaction term is below 0.05. So that's nice. That generally confirms the way that we set up our data simulation to have a significant interaction with no main effects. And it's also interesting to see that the interaction term is identical. So the F statistic and the p-value are the same for the interaction term for all 3 types. Now, the interaction term, the F and the P values for the main effects are slightly different across the three different types, but they are qualitatively the same in the sense that we come to the same conclusion about the data regardless of which type we use. In the book chapter, I go into more detail about the definition and the differences across these three different types. But hopefully, in many cases, you will find that the results don't differ that much. Of course, it depends on what you want to highlight in the data and the characteristics of the data and whether you're focusing on the interaction term. But certainly in this case, and you will see also often in real data, it happens quite often that you try different ANOVA types and you get qualitatively the same results, although, of course, they're different, slightly different algorithms. So the numerical results will be slightly different. As I mentioned in the beginning of this video, the other important conclusion from this exercise is code that you now have to explore multi-way ANOVAs with and without interaction terms. So I encourage you to continue playing around with this code. You can see what happens when you change this number, for example. So now you are creating a situation where there's also a main effect in addition to the interaction term. You can try making these interaction terms smaller to see what size, sample size, and how much variability you need to uncover a small interaction term, and so on. Welcome to exercise 10 of chapter 14. In this exercise and the next exercise, we will explore ANOVAs in real data. So in this exercise, we are going to import the data, create some visualizations, make some predictions based on the plots, and run an ANOVA in Penguin. And then in the next exercise, exercise 11, we will do some visualizations and some correlation analyses to inspect whether the data conform to the assumptions of ANOVA. Okay, so this data set is, it's a cute data set. It's about the impact of vitamin C supplements on tooth length in guinea pigs. So question is, if you give vitamin C supplements to baby guinea pigs, will they grow up to have longer teeth? I guess longer teeth is a good thing in guinea pigs. Anyway, so there's two factors in this study. There's the dose of the vitamin C and the supplement method. So the vitamin C was delivered either with orange juice. I guess they got this in like a cute little cup for breakfast every morning, or directly in ascorbic acid. Okay, if you Google around, you can find this data set online. It's freely available. It comes with the statistics program R. I also have a copy on my GitHub. You can look at the code in my on the online code for this exercise if you're struggling with the, just kind of basics of importing and working with pandas and so on. Okay, so once you get the data in, you want to create a visualization of the data. Should look something like this. So we have the dose of vitamin C on the x-axis here in these different ticks, and the two bars, the two different colors, correspond to the delivery method. So orange juice and directly giving ascorbic acid. Okay, so then on the y-axis, we have tooth length in millimeters. Now, I am not a guinea pig dental physiologist, so I don't really know how to interpret this. But I think it's pretty shocking that there's like a threefold increase or variability in tooth length across these different animals. And you can see that there's really a lot to be said for vitamin C supplements. Okay, once you get this visualization, before running the ANOVA, before looking at the statistical results, I would like you to make some predictions about the results of the ANOVA based on what you see in this plot. In fact, I'm going to make some remarks right now. So if you would like to pause the video and make some observations, make some predictions, then now is the time to do that. Okay, so here are my observations. There's clearly going to be a main effect of vitamin C dose, right? You see in both of these conditions, basically when these numbers increase, these numbers increase. So that's a really clear effect. It's unclear whether it's linear or like a logarithmic relationship, but it doesn't make sense for this to be completely a linear relationship because guinea pigs cannot grow arbitrarily long teeth. You're not going to see a guinea pig with a tooth that is like 10 kilometers long, right? So it obviously can't be a perfect linear relationship, unbounded. But anyway, so that main effect is clear. And then, there's the other main effect of the delivery method, and that is less clear. So for the smaller doses, it does seem like OJ has a better delivery method than ascorbic acid, direct delivery, but only for these two doses. And for this, the highest dose, it seems pretty equal. So therefore, I think I don't know what to expect about the main effect of delivery method, but it does look like there will be a significant interaction between these two because the effect of the delivery method depends on the dose. Okay, so with that said, now I will switch to Python. I'll show you my code and we'll discuss the results. I have the URL for the original data source here if you'd like to read more about the study, and that's also where the citation is. Right now, at the time of this recording, I just put this CSV file on my website, but I'm going to put it on GitHub, so you can check the code for how to import it. Okay, so here we see the data, and yeah, we have the different animals here. This is obviously a between subjects design. So here we have all the different animals in the rows, and then we have the tooth length as an adult, and the delivery method, and the dose. Okay, so those are the data. Here I show the box plot using Seaborn. So this part is pretty straightforward, just running this line of code. If you want to add all of the other dots on there, then that takes a little bit more finagling with the code. Basically, here what I do is extract the data just for this dose and for this supplement method, and len, the column len, corresponds to the dependent variables, the length of the tooth. And then just to make the plot look a little bit nicer, I also set a normal distribution of numbers. So I create random numbers normally distributed to have on the x-axis. That's just to create a little bit of shuffling to get the dots to mix around a little bit. Okay, so here you see the figure, and yeah, this is nothing too shocking because it's exactly what I showed before. I guess I will just mention, you can see these little lateral x-axis offsets of all these white dots. That comes from this variable here. So for example, if I would set the scale up to be higher, then we have a lot more variability. In my opinion, this is way too much variability. You don't even know which condition these dots belong to. And on the other hand, if there's too little variability like this, then that's not so bad. I mean, some people like making visualizations like this. To me, this just, that you get a lot of overlap of the dots. So it's just a little bit harder to interpret with the overlap. So therefore, I like to find this happy medium where there's a little bit of variability. It makes the plot look a little more interesting. It avoids situations like this, where you have two dots with the same numerical value, the same y-axis value. If you don't have any x-axis offsets, then these two will look like one data point. So here you can actually see that these are two data points here. Okay, now it's time to look at the ANOVA. So we have the data, we just input the data frame. The dependent variable is len, length, the length of the teeth, and the two between subjects variables here. Okay, so then we see that we get a significant, basically everything is significant. So the supplement method, the dose, and the interaction term are all statistically significant. Now, as you know from the book chapter, you cannot interpret the main effects when there is a significant interaction without first looking at the visualization. So if you didn't do the visualization first, and you only looked at the ANOVA table, then you would not be able to interpret these until you looked at the graph. So now we can go back and look at the graph again, and we see the main effect of dose is clearly interpretable with or without the interaction term. As I discussed before I switched to code, the main effect of the delivery method is a little bit harder to interpret because we have this interaction here. So this condition where there is clearly no difference between these two. if you'd like, it would certainly be appropriate to do a follow-up series of post-hoc tests with Tukey. Basically, you'd want to compare these two, and these two. And I think what would happen, I don't know for sure because I haven't done this, but I suspect, I mean, this clearly looks different. This is probably also significantly different, and I don't think this is significantly different. Getting back to the question of whether this relationship is really linear or logarithmic or maybe piecewise linear, I think what's happening is that there's just a biological upper limit on the length of the teeth. Your teeth cannot grow arbitrarily long. And when I say you, I mean the guinea pigs. But human teeth also cannot grow arbitrarily long. So I think what's happening is that, somewhere around 30 millimeters is the longest that the teeth can possibly grow, 25 to 30 millimeters. So even if the supplement is working, the teeth just aren't going to grow any bigger than this. So that would be a ceiling effect where it's just not possible to get much bigger than this, except for these guys here. They have these are like vampire guinea pigs over here. Anyway, as you know from reading this chapter, ANOVAs rely on a number of assumptions about the distributions from which the data were drawn, assumptions about the independence of different observations, and assumptions about the model fitting itself, which is that the residuals and the predicted data should be unrelated to each other. That is an assumption that we are going to explore in the next exercise. Exercise 11 is a direct follow-up to exercise 10. So in exercise 10, we computed an ANOVA on some data. And now here in exercise 11, we are going to confirm that one of the important assumptions of the ANOVA is met. And that assumption is that there should be no relationship between the residuals and the predicted data. Now, this is an assumption that I will also get into much more detail about in the next chapter on regression, and we are going to explore it here. So first of all, the correlation between the residuals and the predicted data should be 0. Now, on the one hand, that's basically always going to be true, but you also need to visualize the data to see not only is there no linear relationship, there's also no nonlinear relationship. So there should be no relationship whatsoever between the residual and the predicted data. So what you need to do in this exercise is to compute the predicted data and compute the residual, and then make a graph of one by the other that looks something like this. So here we have the residuals on the y-axis and the predicted length of the tooth on the x-axis. Now, why are there so few possible values for the predicted length? Why don't we see a cloud like this? Well, remember that in an ANOVA, the model of the ANOVA is that all the data within each cell are equal to the mean of that cell, and any deviances, any variation outside the mean is due to noise. That is the assumption of an ANOVA. Anything that is not the mean of the cell is noise. So that means that the number of possible numerical values for the predicted data equals the number of cells. So we have a 2x3 ANOVA, so we should have 6 possible predicted values. So here's 1, 2, 3, 4, 5, and it might look like something is wrong, but actually you can see these dots are all perfectly vertically aligned, perfectly vertically aligned. Here it looks like there's some jitter. There's not actually any jitter. What's actually happening here is these are 2 predicted values that are just really close to each other. And if we scroll up to the graph of the raw data, that corresponds to these 2. So you see the means of these 2 conditions are really close to each other. And so therefore, the predicted means are also going to be very close to each other. And that's what you see here. Okay, so that's your goal. For this exercise, I will make some more interpretations and comments about this figure when I show you the code to produce it. So here is how we can compute the predictions for the data. It is literally just the mean of each group, each cell. So I use this method called group by. So I'm going to group the data frame by these 2 variables, and then I want the dependent variable, which is the tooth length, and then apply the transform of the mean. So this is going to give a new column in the data frame, that is the prediction, which is literally just the mean of each cell. So that is our predicted data values. Okay, and then to get the residuals, we literally just take the difference between the observed data and the predicted data. So here we have the observed data and here we have the predicted data. Literally just subtract them and that gives us the residuals. So actually pretty straightforward. And I will discuss this in more detail. You will see this kind of stuff again, computing predicted data and residuals, relating that to the observed data, again in the next chapter. So here you see the data frame. This is just a, selected rows, just every fourth row. And yeah, just to show you that we also get the predictions and we get the residuals in these data. So now what we want to do is pretty straightforward. We just want to make a plot of the predictions by the residuals. And that's what I do here. So I plot the predictions by the residuals. And here I'm also computing and reporting the Pearson correlation coefficient between these. And yeah, there you go, just like what I showed. Now, what you're looking for in this residual plot is some kind of like fanning effect. If the residuals were small over here and they got big over here, I mean, maybe you see that a tiny bit, but these residuals are also dispersed. So if you don't see structure, then that's a good sign. If you do see some really obvious nonlinear structure, some bends, some curves, some lines, I'll show you more examples in the next chapter of what violations of this assumption look like. But then you should be a little bit concerned. But to me, this looks great. The Pearson correlation is 0, although you'll learn in the next chapter that it is trivially 0. It's always 0. But you still want to compute the correlation and look at the residuals plot to make sure that you don't see any obvious structure.